So in the last video lecture, we looked at some special cases. We looked at the derivatives of exponential functions and logarithms. And so today we're going to transition kind of back to multiple types of functions instead of just special cases. So we're going to look at the product and quotient rules. Okay, product meaning multiplication, quotient meaning division. So remember we had a sum or difference rule, but these are going to be a little more involved. So if we're taking the derivative of one function times the other, it will be the first function times the derivative of the second plus the second function times the derivative of the first. Okay, and when I am teaching students this for the first time, I literally have them memorize the words here. It's first times derivative of the second plus second times derivative of the first, rather than trying to remember this F and G notation. It can be a lot easier often to just remember the words. Okay, so anytime we are multiplying two functions, we're going to use this product rule. So let's say that I was asked to find the derivative of f of x equals 2x squared minus 1 times x cubed plus 3. Now, technically speaking, I could FOIL this out and then find the derivative, but I want to show it using the product rule. So notice this is a first function times a second, hence the product rule. We're multiplying one times the other. So remember, anytime we're going to find the derivative, we want to say f prime of x. So we're going to start off with the first function. Notice no change is made. Okay, so this is the first. Okay, and we're going to multiply by that by the derivative of the second. The derivative of the second function would be 3x squared. Remember, the derivative of 3 would be 0. So this is going to be the derivative of the second. And then plus the second with no changes made, notice, times the derivative of the first. So be careful, the derivative of this one would be 4x to the first. Remember, the derivative of that is 0, so it would just be simply 4x. So this would be the derivative of the first. So that's how we use the product rule, and then the rest is just algebraic cleanup. So we can do distributive property back this way. I know we're probably used to doing it the other direction, but we can multiply this times both things, and then also this times both things. So if we do that, we're going to get 6x to the fourth, right? 3x squared times 2x squared. 3x times negative 1 is minus 3x squared. This times this, so 4x times x cubed is 4x to the fourth. 4x times 3 would be 12x. And then go through and look for like terms. Notice we have a couple here and here. So in the end, our reduced answer is 2x to the fourth minus 3x squared plus 12x. Sorry, no exponent there. Okay, and remember, this is always representative of the equation for the slope of the tangent, always. When we are being asked to find derivative, that is what we're finding. Okay, so let's practice maybe a couple more of these. Maybe we'll throw in some of our special cases from the last video lecture. So this is x cubed times e of x, or e to the x, sorry, e to the x power. It's important to note that these are two different functions. Anything with an x in it is its own function. So I have first function times the second. So anytime you have one function times another, the product rule is in order. So if I want the derivative, it will be first, right, times derivative of the second. But remember last video lecture, what was the derivative of e? It was just itself. So far this is the first, right? And this is the derivative of the second. And then the formula for product rule says, then I do plus the second times the derivative of the first. And I'm going to put that in parentheses just so we realize that that's all of that together. So this would be the second, and this would be the derivative of the first. So if you multiply this out, there's really not a whole lot you can do, but you could say this is x cubed e to the x plus 3x squared e to the x. Typically you would write the x terms first and then the exponents last, okay? But a lot of times in my math lab they're going to want you to simplify, so notice this has an e to the x in common that you could factor out, and also an x squared. And if you factored out an e to the x and an x squared out of this term, you would have x left. If you factored out an e to the x and an x squared in the last term, you would only have a 3 left. So I'm going to circle both of these. Honestly, on test 1, I would be just fine with this notation, but I think that my math lab is probably going to want this. Okay, so if you want to, you can put a times there so you don't get confused with the fact that we have x's and e to the x's. All right, so let's do another where maybe we pull in a special case from last time. So find the derivative if h of x is equal to 3x to the fourth and then ln of x squared. So it's always helpful when you're first starting to identify what you think is the first function versus the second, because then your derivative formula means a little more. So we'll do first. Notice I'm using parentheses anytime there's more than one piece inside a part. First times derivative of the second. Okay, so you need to think about that. Remember when we did derivative, that 2 moves out to the front because it's a natural log, and then the derivative of ln of x is 1 over x. So this is first, and this is derivative of the second. Okay, go back and review that from the last video lecture if you're not sure how I got the derivative of the natural log of x squared. So I'm not quite done, right? Plus the second times the derivative of the first. The derivative of the first would be 12x cubed if you moved the power out to the front and you reduced the power by 1. So this would be second, and this would be derivative of the first. Alright, so again, I'm going to write it as simplified as we can, and then I'm going to show you an alternative way that my math lab might want. So you do need to simplify. For instance, you can do 3 times 2. Okay, 3 times 2 is 6. So you're going to get 6, and then x to the fourth times 1 over x would get rid of one of the x's. So this would be x cubed. And then if we simplify this, again, we usually write the e or the logarithm portion second. So I didn't really do any combining here. By the way, you can't combine these. This is ln of x squared. It's its own thing. Okay. But again, my math lab is going to want you to look at this and say, hey, both of these have a 6. They both have an x cubed. And if you were to factor that out, you would get 1 plus 2 ln of x squared. So when I circle both forms, it really means that either form on a test for me would be okay. But my math lab is sometimes kind of particular in how it wants an answer, so keep that in mind. Alright, so let's do one more and then we're going to look at the quotient rule. So find the derivative when f of x is equal to 2x plus x squared times x cubed plus 4x. It's easy to pick out what the first and second functions are when they give you a parentheses. Clearly this is what they're wanting you to call the first function, and this is what we'll call the second function. Alright, so let's go kind of slow here. So use parentheses. we have first times derivative of the second. So derivative of the second would be 3x squared for the first part. The derivative of 4x is just 4. Okay, so this is the first. This is the derivative of the second. And then I still have to go plus the second times the derivative of the first. So the derivative of this would be 2, right? 2 for this, and then plus 2x here. So parentheses are super important on a problem like this. So I tend to put them always when I have more than one part to a piece of my problem. And then notice we can FOIL to simplify here. So that's probably not going to be your favorite part of this problem, okay, but we can algebraically do it. We're all learning business calculus, so we can do the algebra portions. So we're going to have two cases of FOIL, right? One here, one here. So let's go slow. 2x times 3x squared is 6x cubed. 2x times 4 is 8x. X squared times 3x squared would be 3x to the fourth. And then last, x squared times 4 would be 4x squared. And now let's do FOIL again. First times first is 2x cubed. Outside, x cubed times 2x would be 2x to the fourth. Inside, 4x times 2 would be 8x. And then last but not least, 4x times 2x would be 8x squared. Notice there's lots of opportunity for you to make exponent errors here, so you just want to go slow enough where you don't make those errors. So this is how I usually combine like terms in a problem with lots of terms like this. I'll go through and start with the biggest power and underline them. So notice I have 2x to the fourths, right? So I have 3, or 2x to the fourth terms, by the way. 3x to the fourth plus 2 more would be 5. But then once I'm done with them, I kind of just get rid of them. That way I'm not looking at them anymore. Okay, so now let's go for the x cubed terms. Notice I have 6 of these plus 2 more, so that would be an 8 for my total. So now those are gone. I have 4x squared plus 8x squared for a total of 12 of them. And then last but not least, 8x plus 8x would just be 16x. Okay, so remember, this time and every time, this is still, as complicated as it is, the equation for the slope of the tangent line. Alright, so when you're multiplying two terms, we use the product rule. When we are dividing two terms, we use the quotient rule. So we're going to look at the technical form of the quotient rule, and then I'm going to give you kind of the everyday explanation that I like to use. But we use the quotient rule when we are taking the derivative of two functions being divided. And so the process is, it's the bottom function times the derivative of the top function minus the top function times the derivative of the bottom function, and then all over the bottom function squared. This product and quotient rules are rules you're going to need to commit to memory as soon as possible. You're definitely going to want to know them for the test. So let's write this out in words. So it's bottom times derivative of the top minus the top times the derivative of the bottom, and then all over the bottom squared. When I do the quotient rule, I actually say these words in my mind as I write down the different parts. It makes it just a lot easier, and it does help you commit it to memory quicker. So let's look at some with the quotient rule. So I want you to find the derivative if our function is 3x plus 2 over x minus 1. The good thing about the quotient rule is it's very clear what the top and the bottom are. You don't have to worry about what's the first function, what's the second function. Alright, so the derivative is, we're going to go slow, okay, so it is bottom times derivative of the top. So what would the derivative of 3x plus 2 be? It's 3, okay, minus the top times the derivative of the bottom. I'm going to go ahead and put that in parentheses also. The derivative of x minus 1 would just be 1. And then it's all over the bottom squared. Okay, so let's make sure we do distributive property. You will need to make sure this 3 goes to all of these things. This 1's not going to affect anything, but keep in mind this negative sign will. So if we do all of those things, we're going to get 3x minus 3 for this, right? 3 times x minus 3 times 1. And then here we're going to get minus 3x minus 2. And then over the bottom squared. The nice part about these is, for the most part, I won't really ask you to work with the bottom. You can just leave it factored. It's already usually going to stay that way. So the 3x's will go away. And in the end, you just get negative 5 over x minus 1 parentheses squared. Okay, and sorry if this is redundant, but the sooner you learn this, the better. This is still the equation for the slope of the tangent. Okay, so let's look at some more where maybe we throw in some of the ones from the last lecture. So I want you to find the derivative if f of x equals the natural log of x over x squared plus 3. So you may not really like how this one's going to look in the middle. Again, if you'll just take it slow. If you need to pause the video as you go, you can do that. So we're doing quotient rule, right? So it is bottom times derivative of the top. The derivative of natural log of x is one of our special cases. That derivative is 1 over x. Minus the top. Okay, notice I didn't change the top, right? Times the derivative of the bottom. So what's the derivative of x squared plus 3? So it's 2x. And then it's all of that over the bottom squared. Alright, so what we're going to get here is we're going to get x cubed plus 3 over x when we simplify this first little group. We're going to get minus 2x times the natural log of x here. And then on the bottom we're going to get x squared plus 3 parentheses squared. Notice I'm really not ever messing with the bottom that much. However, I do need to work out the top. My math lab wants simplified answers. So if I write that over 1 and I remember way back when I did fractions, I want a common denominator, so I need this denominator to be x to match this one. So to accomplish that, I'm going to multiply by x over x. That's really just like multiplying by 1. So that's going to give me x squared plus 3 over x minus 2x squared, right, because the x is going to combine with the 2x, times natural log of x over x, and then over that same denominator that hasn't changed yet. So the point of me combining those, remember, is, or the point of me getting common denominators is so I can combine them. So now I get x squared plus 3 minus 2x squared times the natural log of x over x, and then over the denominator. So just to recap, all I did in that last step is just condense these two fractions with common denominators to a single fraction. And then in the end, this really just is a denominator, so I'm going to circle this. This is a denominator, and so is this. So when you have a problem like this, you can condense it a little bit more. So notice the numerator is going to stay. By the way, I cannot combine these x squared terms because of this ln of x connected. They're not like terms. But I can kind of condense these two denominators together, and I'm just going to multiply them. So you can say it's over x squared plus 3 squared. So essentially you're like saying I had two parts to my denominator, and now I've kind of condensed that into one denominator. So I know this is ugly, but that's as far as we can go with that. And even that ugly mess is still the equation for the slope of the tangent. Don't forget that. All right, let's do one more quotient rule, and then we're going to review some of the previous problems we've done, or the types of problems we've done using these new rules. So remember this dw notation. We haven't had that before, but normally we see it as dx, but all the dw indicates is we're using the letter w rather than the letter x. Okay, so no real change there. We're still being asked to find the derivative. So the derivative is, notice this is a different format, so I don't have to write f prime. It wouldn't make sense anyway. That's not what I have here. The derivative is going to be bottom times derivative of the top, so be careful. Derivative of the top would be 4w cubed minus 3w squared. So I have bottom times derivative of the top minus the top times the derivative of the bottom. So the derivative of 3w minus 1 is just 3. And then all of that mess over the bottom squared. So we are going to need to simplify this. So we're going to use FOIL here, and we're going to use distributive property here. Make sure you know that we have a negative sign that's distributing, but we also have this 3 that's distributing as well. So one way to think of that is we're really just multiplying by a negative 3, and that's probably the easiest way to think of it. So let's do FOIL slowly. 3w times 4w cubed would be 12w to the 4th. Outside, 3w times minus 3w squared would be minus 9w cubed. Inside, negative 1 times 4w would be minus 4w cubed, or minus 1 times 4w cubed rather. And then last, negative 1 times this negative term would change it to a plus. And then remember, we're really like multiplying through by negative 3. So this is going to be negative 3w to the 4th. Plus 3w cubed, and then again it's all over the bottom squared. So kind of like before, look for like terms, and then maybe we'll just simplify or mark them out. So 12w to the 4th minus 3 of them would be 9w to the 4th. So if I want to, I can get rid of those. So I have minus 9 minus 4 more, that would give me negative 13, but then plus 3 would give me plus 10 of them. So all my cubed terms are taken care of. And then the squared term has nothing to combine with. And again, notice in all of these, we are not really messing with the bottom at all. We're really just simplifying the top. So I would venture to say it's probably the algebra that's going to cause you a little bit of issue, if anything. Once you learn the product and the quotient rules, they're really not so bad, but the algebra involved can be a little hairy. All right, so let's look at some old problems that might use these new rules. So let's say that I told you to find an equation of the tangent line to the graph at x equals 2. And let's say that the function I give you is f of x equals 7 minus 3x times 1 plus 2x. So first let's talk about what to do here. If you see the equation of the tangent line, that should automatically tell you, hey, I'm going to need to do something with derivative. That is the definition of derivative, the slope of the tangent line. Okay, so the first thing that we need to do is we need to write an equation of a line. So we've already done this before this semester. So recall we want to use this formula, point slope. Okay, and we need two things to use point slope. We need the slope, and we need a point on the line or on the curve. So let's go through. How are we going to find the slope? Well, we're going to find the slope by finding the derivative. Okay, so slope means, hey, find the derivative. Notice to do that, I'm going to need to do product rule, right? Because it's one function times another. So it's first times derivative of the second plus the second times the derivative of the first. Notice I didn't label this one. If you want to continue to label, you sure can. But now I'm going to do distributive property here and here. So I'm going to get 14 minus 6x minus 3 minus 6x. So in the end, the equation for my slope is going to be negative 12x plus 11. So I'm going to circle this. This isn't exactly as far as I need to go, but it'll at least tell me how to find my slope. Okay, this is the equation of the slope of the tangent. So now I can plug in 2. So if I want the slope at x equals 2, I need to do f prime of 2. In other words, plug 2 into that derivative. So it's going to be negative 12 times 2 plus 11. So negative 13 is my slope. So I'm going to circle that. That is half of what I need to write the equation of the line. Okay, but I still need to find, so we found the slope, right? So now we need to find the point. And we already have half of the point. We know that x is 2. So to find y, we need to plug in 2. You always find y by plugging it into the original function. So if I want to know the y when x is 2, I just need to plug it into the original function. So f of 2, so it's not really on screen. Let me move it back down. So we're going to plug 2 into this equation. Okay, and we'll keep the parentheses and all. So it's going to be 7 minus 3 times 2, close that parentheses, times 1 plus 2 times 2. Make sure you do order of operations, right? So you're going to get 7 minus 6 or 1 for the first parentheses. You're going to get 1 plus 4 or 5 for the second parentheses. So I get a y value of 5. So the point I'm looking for is when x is 2, y is 5. So now we have everything we need. We have a slope, we have a point. So let's plug it in my y minus y1. So y minus 5 equals the slope times x minus 2. And then we'll just do a little bit of arithmetic, right? So we're going to multiply through here. So we get y minus 5 equals negative 13x plus 26. And then last but not least, add 5 to both sides. So in the end, we get the equation of the line to be negative 13x plus 31. Notice, past the point of finding the derivative using the product rule, we've already done problems like this before. Okay, so it's just new and different ways to find the derivative, but then we're doing similar things as we've done previously. All right, so let's look at maybe one with a little bit more unusual. So I want you, or a little more unusual look, I want you to find the slope of the tangent at x equals 4 for the function f of x equals 4x to the 1/2 times x squared minus 2x. So notice, this wording, again, means derivative. Okay, slope of the tangent means find the derivative. So notice I will have to use which rule here? I'm multiplying this term by this term, right? So consider this to be my first function, and this is my second. So I'm going to use product rule. So the derivative is going to be first times derivative of the second. So what's the derivative of this guy? It is 2x minus 2. Really important that you use parentheses there. Plus the second times the derivative of the first. So we're going to go slow on this one. If you move the power out to the front, you'll do 1/2 times 4, which is 2. And if you subtract 1 from the power, you're going to get negative 1/2. So this is first. This is derivative of the second. This is plus the second times the derivative of the first. But here's where this one gets a little algebraically ugly. And I know I say that a lot, but actually it's pretty common in calculus that it's actually the algebra that trips us up. So we just want to be careful about that. So we want to do distributive property, but you're going to need to remember your power rule for exponents. In other words, how do you combine terms when you have powers for x? You add the exponents. So if you do 4 times 2, of course you get 8. But if you do x to the 1/2 times x to the first, you would add those exponents. So if you add 1/2 plus 1, you actually get 3/2. I know that's weird, okay, but that's what you would have here. And then 4x to the 1/2 times minus 2 would be minus 8x to the 1/2. So it's just distributive property. And then here, same thing, right? This term times this one. So I have 2, right? But then if I add these exponents, so what's negative 1/2 plus 2? Notice it's a repeat of what's something I've already gotten. And then if I do this times this, I'll have a minus 4, right? 2 times 2 is 4. But then if you add negative 1/2 plus a 1, you're going to get 1/2. So if you must, use your calculator, but you should be able to add things like 1 and negative 1/2 without a calculator. Now we do have some like terms, so the derivative equation, it looks like 10x to the 3/2 minus 12x to the 1/2. So the slope at x equals 4 is going to be whatever I get when I plug in 4 to my derivative equation. So it's going to be 10 times 4 to the 3/2 minus 12 times 4 to the 1/2. If you remember that 1/2 power is really just a square root, you might be able to do this one without a calculator, but we have a calculator, so let's use it to our advantage. Okay, so we have 10 times 4 raised to the 3/2 minus 12 times 4 raised to the 1/2. Okay, and so if you do all of that together, you get 56. So in other words, the slope is quite steep at x equals 4 for this equation. All right, so last but not least, let's do a problem where we maybe do an application, maybe a business application. So sales of a newly released DVD can be described using the following function. So let's say that function is s of t equals 90t squared divided by t squared plus 50, where t is the number of months since the DVD was released. And S of T is in thousands of DVDs. So in other words, you're going to have a big change in the sales of DVDs depending on how old the movie is, right? We're going to assume for the most part that DVDs that are older probably won't sell as much, right? New releases typically sell better than older releases. Okay, it's not always the truth, but pretty close. All right, so I'm going to ask you two questions. The first is, I want you to tell me the rate of change of sales 10 months after the release. So, this terminology should tell you what to do. Rate of change means slope, right? It means derivative. So we're going to find the derivative of S of t. So notice that looks like S prime of t. Notice if you look at this, it's a quotient, right? It's something divided by something else. So yes, I'm going to have to use the quotient rule. Okay, so let's go slow. Bottom times derivative of the top. The derivative of 90t squared would be 180t minus the top times the derivative of the bottom. So what would the derivative of t squared plus 50 be? It would be just 2t, right? Because the derivative of 50 would be 0. And then all of that over the bottom squared. Just as usual, remember we're not going to mess with the ugliness of the bottom, but we are going to use distributive property here. Remember there's actually a negative there, so keep that in mind. So if you do distributive property, this times this would be 180t cubed. Use your calculator if you need to. 50 times 180t would be 9,000t. And then don't forget we're changing sign to a minus, right? But 2t times 90t squared would be 180t cubed. And then don't forget to include your bottom. So in this case, notice I have a nice cancellation, right? These terms go away. So I end up with 9,000t divided by that denominator. So this is my rate of change formula. But notice this problem specifically asked me for the rate of change 10 months later. Okay, that means time is 10, right? So I need to actually find, I'm going to put a star by this. This is what I'm actually asked to find in this part. So I'm going to plug in 10 to my slope equation. So 9,000 times 10 on the top, parentheses 10 squared plus 50, and then that whole thing squared on the bottom. So use your calculator, but you get 90,000 on the top, you get 22,500 on the bottom, and this works out to be 4 when you reduce it. But just remember that this is the rate of change in thousands, because if you remember the problem, S of t was in thousands. So you always want to go back and read the word problems. A lot of times we will have the problem in millions or thousands or something like that. So what this means is because it's positive, we are increasing at this stage. We are increasing by 4,000 DVDs per month. Notice a rate of change should always be per a time period. And notice if we would have gotten a negative number, it doesn't mean worse. It doesn't mean, you know, the sales are negative. It means the sales are being reduced. They're not increasing at this time. So what if I instead, though, asked you for the sales after 10 months? So on test 1, I'm going to want you to be able to tell the difference for when I'm asking for derivative and when I'm not. Okay, so in part A I said the rate of change, but in part B I'm not saying the rate of change. I'm just asking for the straight up sales. So we will not use derivative here. So don't just assume that we're always using derivative just because that's what we happen to have been doing for a while. Okay. For this one, you would just use the original equation and plug in 10. That's our sales, right? If you want to know the sales equation, it's what we were originally given. So it would be 90 times 10 squared over 10 squared plus 50. So in the end, you'll get 9,000 over 150. So you'll get an answer of 60. But remember, this is not 60 DVDs. That wouldn't be very many, right? It's actually 60,000. So this means that there are 60,000 DVDs that are sold in the 10th month. So since the rate of change at this stage is 4,000, we would expect the next month to be about 64,000 DVDs since we would increase by 4,000. So make sure as you're reading through these problems that you pay attention to whether it's asking you for derivative. To be honest, most of the time it is, but we don't want to make that assumption. Okay, sometimes it's not asking us for derivative at all.